Thank you. So let's a little bit recap what we finished yesterday with. So if you remember, we introduced for the first time the notion of inflation, which is defined to be the period of during the evolution of the universe for which a double dot is larger than 0. And we motivate this period solving the horizon problem that graphically, I didn't draw the picture yesterday, but graphically, what does it mean? It simply means that we have a region that today has an Hubble radius, which is h0 to the minus 1. And then we impose the condition that if we contract this region back in time, this region has to be contained in a region where the Hubble radius was h star to the minus 1, where h star was the Hubble radius during inflation. Okay, so that was the idea. We want to contract our universe back in time in such a way that is contained in a small Hubble radius at that time, in such a way that all the regions that will be emitting photons from all over the sphere will be contained in the same region, and therefore they were causally contact. Okay, so that was the idea that we imposed yesterday, even though mathematically we found a condition that if we define as also Matteo did yesterday, dn to be h times dt, in such a way that if h is constant, we can write down the n, which is the number of e-folds, by which inflation lasts, which is, in this case, h star times tf minus ti. If you simply integrate this equation here, we discovered that, in fact, in order to have this picture realized, more or less n has to be larger or about than 60. Okay, and yesterday Matteo found the correct number depending upon the value of h star, depending upon the value of the heating temperature and so on, but it's in this ballpark. Okay, so that was the idea. And then let me go back for a few minutes to this, also to an exercise that Matteo did yesterday, where he computed basically the behavior of omega minus I, minus 1 to during inflation. So the idea, if you remember, was to start from omega minus 1, which is k over a square h square. We discovered that during radiation, this object goes like a square, and the reason is because h square goes like a to the minus 4. And we discovered that, in fact, in order to explain the value today, if we plot omega minus 1, let's say that this is T0, this is some Tf, which is going to be identified with the end of inflation. Let's say we plot omega here, so we have 1 here. We said that in order to go to explain the universe today, we need to go to a value of omega minus 1. Let's say in the standard model, let's put Sm, which has to be about 10 to minus 62. Okay? So this number has to be so close to 1 by a factor 1 over 10 to the 60 or so. So the idea of the inflation is, in fact, that to consider this point not as an initial point, but in fact there is another period which goes from the beginning of inflation to the end of inflation, where in fact this number, 10 to minus 62, is obtained squeezing this omega minus 1 to this value. So during inflation, supposing that it took place, what happens is that omega minus 1 has a different behavior because the Hubble rate is constant, so we can put a star here just to indicate that it's a constant. And of course, we discover that this guy goes like a to the minus 2. So you see, with time, it goes down rapidly to a small value. And in fact, if we know that a goes like e to the h star times t minus ti. So it goes like, so the total number of e-folds will be e to the, it will goes like e to the n. We will obtain e to the minus 2n here. And if we impose this number to be 10 to minus 62 or something, we get again n of order of 60. So what inflation does, it takes your universe, which is closed or open or any global geometry has, and then he basically, the omega minus 1 is driven to 0 because it goes like e to the minus 2n. So you start from a given value which is different from 1, and then it goes back to 1 very, very rapidly, in fact exponentially, and that is going to be the initial condition for the standard model cosmology. Okay, so that is the idea. This is what you have seen also yesterday in the in the exercise session. Now I want to make a crucial point here, which is the following. So inflation, so the statement that I want to make is that inflation does not change the global geometry, only the local one. What does it mean? It simply means that if the universe globally has a geometry of a sphere, let's say if k is equal to +1, let's say. If k is equal to +1, this is just an example, the universe is globally has a geometry of a sphere, okay? Inflation does not change this. Inflation simply takes the spheres and it makes it incredibly large, okay? So it increases this by a factor, enormous factor. Let me draw it like this. So here is the beginning, then at the end, you have increased the scale factor or by the factor e to the n. So it makes the sphere incredibly large, such that locally, if I take our universe today, our local universe, so this is a section of h to the minus 1, locally, the geometry is very flat. It looks like a Euclidean geometry, okay? Because if you take a sphere, you increase the radius by an enormous factor. Locally, of course, your surface is very flat, but it is still a sphere, okay? So the universe is still closed. Locally, so in this region that we can observe, it is flat. If we had a way to go through all the sphere and compute, for instance, the surface, we will discover that it's 4 pi times the radius square, okay? The same if it was an open universe, like a saddle with a negative curvature k equal to -1. So locally, we expect a flat universe, and in fact, this is what we measure. Current measurement gives us omega -1 up to with an accuracy of less than 1%. So locally, our universe is very flat, but we don't know if globally the universe is closed, open, or flat. Okay, so that inflation does not tell you. In fact, what is going to happen in models of inflation which are reasonable, what happens is that the number of e-folds that you can compute, I will do a simple estimate afterwards, but the number of e-folds is much larger than 60 usually. Okay, for instance, we will see that the number of e-folds for the phi square model is 10 to the 10 to the 12. Okay? So inflation lasts in terms of e-folds a large number in such a way that in fact omega -1 at the end of inflation is not equal to 10 to -60, but it's much smaller than this. And of course, when the standard cosmology starts again, it will never be able to recover a value which is close to 1. Okay, so inflation predicts in most of models that really our universe has to be omega equal to 1 with enormous precision, okay? A precision that, of course, observationally we will never reach, but that's the theoretical prediction of inflation, okay? So that was a comment that I wanted to make, because there is sometimes some misunderstanding on this. Of course, if you construct a model of inflation where the number of defaults is about 60, then you might expect some deviation from unity. Okay, that's completely reasonable, but it's very difficult to construct a model of inflation where the number of defaults is limited to be the right amount to solve the horizon problem. Okay, so that is what most of the time is happening. This concludes somehow the session that I call the problems of inflation, the problems of the standard model and the solution by inflation. So from now on, what I will do, I will try to go to explain to you how we realize inflation, and I will take the simplest route of a scalar field. But let me pause for a second, ask if you have any questions or comments or curiosities or criticism. Yes. Yes. Way higher, yes. That's exactly the point. Yes. No, there is not. No. In fact, as I said, in the simplest model, you get this number. But then, of course, there is also another concept that I won't talk about, which is the idea of eternal inflation, the fact that in some regions, inflation never stops. So in our horizon, at some point, luckily, inflation stops, because, of course, otherwise we will not be here. But in other regions, inflation continues, and it might continue even now. So the regions which are, of course, causally disconnected from us, we will never see them, but still, it's happening for eternity. So no, there is not such an upper bound. Yeah. Using what? Monopoles was the original historical reason why, but using monopoles to drive inflation, or yeah, there are ways to drive inflation which are not standard in the way that I will teach. Like, for instance, you can have a topological defects where, yeah, like cosmic strings, where inside this string you have a false vacuum that will inflate and the external not. But those are, as I said, non-standard and interesting, but I don't have time to teach. Otherwise, it will take hours. Okay. Any other question or comments? Yes, please. Yes. Yes, the local one. Correct. All right, so let me go to the background. So let me do this. So for the time being today, at least the large majority of the lecture, I will teach now. I will go to the. I will forget about the perturbations. That will be the subject of the next lectures, and I will take care only about talk about only the background. Okay, so we said that inflation by definition is a double dot larger than 0. We also said that there is an equation that you can derive from Einstein theory, which is a double dot divided by a minus 4 pi g Newton divided by 3 rho plus free pressure if you have an ideal fluid. So this, you discover that from here, that has to be larger than 0, so the pressure has to be smaller than minus rho over 3. And yesterday, if you remember, we took the extreme case in which the pressure was equal to minus rho. And then I told you to stay with me, just assume that this is true, and then we will explain why, and exactly what I want to do now. I want to go back and see why this assumption that we took with p equal to minus rho, that was giving this exponential growth, was motivated. As I said, there are many ways to derive inflation, but today what I will do, and also the next lecture, I will take the simplest approach. Let's assume that there is a scalar field, which from now on I will call it phi, okay, which is a function of x and t. This scalar field is called inflaton, with no fantasy at all, because it's the field that is driving inflation. okay, as we'll see in a minute. So I will call it inflatone or scalar field from now on. Now, this scalar field has an action. Of course, it's an action in coarse space-time, so I have to be careful about the metric as well. So the scalar field has a metric, as an action, which is S of phi integral in d for x of the square root of minus g, which is the determinant of the Friedmann-Robertson-Walker, which I'm going to take to be, as I said, minus dt squared yesterday plus a square of t times dx squared. Okay, so that's my metric, my background metric. And then I have minus 1/2 g mu nu, the inverse metric, d mu phi minus v of phi. You might not be familiar with the signs here, but remember that I'm using this convention minus plus plus plus. Okay, so it's just a convention. You could use a plus minus minus minus. In this case, what you will have, you have a plus here and a minus there. Okay, so once you have this scalar field, what I can do, I can compute the corresponding energy momentum tensor, which is T mu nu with the indices down. It's minus 2 divided by the square root of minus g times the variation of the action with respect to delta g mu nu with the indices up, of course. And this turns out to be d mu phi minus, or sorry, plus g mu nu times the Lagrangian, where the Lagrangian is nothing as the same piece without the square root. And then, if you now assume that there is only a scalar field, which is only the homogeneous part, so what I'm going to do, I'm going to assume from now on that my scalar field is only the homogeneous part, so I neglect about the displacement in the part which depends on x, on the pace, and then I assume that there is only a function of time, so I consider only the background, and in order to remember, to recall that there is an homogeneous part, I put a 0 here, okay, from now on. Sometimes I will forget, for sure, but you will correct me, okay? So this is just the background in such a way that this object here, if you compute, this guy will become diagonal, and here you will have rho, p, and p. Well, rho is going to be, if you do the computation, is 1/2 phi dot 0 square plus v of phi 0. And the p is the same thing, but with a critical minus sign in front of the potential. So there is a minus here. Okay? So I don't do the exercise, but it will be easy to do. You just plug the indices, knowing that g mu nu with the indices down is -1 a square, a square, a square. Okay? So that is the basic quantity that we need from now on. All right, so now this scalar field, whatever it is, it might be the Higgs field maybe of the standard model, has a potential. So if I now compute the equation of state of this field, so the equation of state W is P over rho, is going to be 1/2 phi dot 0 square minus V divided by 1/2 phi dot 0 square plus V, okay? And let me also specify that this is only a function of phi 0. Okay, so that's a generic formula. But now I decide, so I impose to the system that the potential of phi 0, if I plot it, I impose that this potential has a minimum, let's say, the simple, and then it's when I go to large values, it becomes very, very flat. Okay, suppose that I'm able to construct a model in such a way that this potential becomes flat. Of course, this is just an example. You could have potential which are different from this, but this is just an example. So let's suppose that my scalar field lives here and is slowly rolling down to the bottom of its potential. And let's suppose for the time being that I can neglect the kinetic energy, because of course this guy is moving very, very slowly because this is a plateau. So in this case, that if I do the approximation that phi dot 0 square divided by 2 is much smaller than V of phi 0, because I impose the potential to satisfy this condition, and I will quantify a little bit later what that means, this ratio becomes of order of -1. Okay? So with a simple scalar field, whatever it is, as long as the potential of this inflaton field is probing a region of the potential where the potential is extremely flat, the effective equation of state, which depends of course on time, it's roughly equal to -1, which is exactly what we want. During this period, as long as this ratio is close to -1, inflation will take place. So the universe will expand exponentially. But of course, at some point, when slowly the field arrives in a region where this condition is broken, because of course here the field will start fast rolling down towards the bottom of the potential and eventually oscillates, inflation will end. Okay? And that's the reason why at some point inflation lasts for a number of efforts, which is basically more or less the region where the inflation is probing the plateau, and then inflation ends. Okay? An exact de Sitter period where the potential is exactly constant is the region where P is equal to -1 exactly, because the field is not moving, of course. But in this case, inflation will never end. So that's not the region that we are concerned with, because we want inflation to end. Okay, so this is more or less the idea of course, who is this inflaton field and how you get such a potential. That's another complete different story, which I will not discuss, because it involves model building of inflation and so on. So I will give you one example, maybe later on, if I have time. But for the time being, let's just assume that this scalar field exists. Let's assume that as a potential, and let's characterize now what are the conditions for which this is happening. Okay, so how do I quantify this? Well, in order to do this, what I have to compute is the equation of motion of the homogeneous part of this scalar field. So you do the usual Euler-Lagrange trick. So you write down the equation of motion as d mu, the variation of the Lagrangian with respect to d mu phi, minus, of course, the variation of the Lagrangian with respect to phi, equal to 0. If you do this, knowing that the Lagrangian is the one that I wrote before, for the homogeneous part, you get an equation that, so remember that phi 0 is only a function of time, so you get phi double dot 0 plus 3h phi dot 0 plus v prime of phi 0 equals 0, where for me now the prime, v prime, means the derivative of v with respect to phi 0. Okay, and the dot is the derivative with respect to time. Where does this free h comes from? The free h comes from the fact that if you remember, the Lagrangian has a square root of minus g in front, okay, which is, of course, it is equal to a cube for the metric that I'm using, okay, that one that I wrote there. It's a square, square root, so a cube. And therefore, when I take the derivative, for instance, if I put mu equals 0 here, I take the derivative, I also have a term to derive, which is a cube with respect to time, and the derivative of a cube will give me 3 a square a dot, and then I collect the a cube, and that will give me 3 a dot over a, which is exactly 3h. So during the evolution of the universe, the scalar field does not only follows according to the potential, to the steepness of the potential, but also has a friction term, which takes into account the fact that at the same time the universe is expanding. Okay, so that's an equation of motion that you have seen many times, so like an oscillator, but there is also a friction term, so it's basically an oscillator with a friction term as well. So just simple oscillator, of course, if the potential is quadratic, but in general, we don't know what the potential is in this case. Okay, so that's the equation of motion of the scalar field, of the homogeneous part. And now I want to use these equations here in order to quantify or to simplify the solution of that equation in order to compute at the end, for instance, the number of efforts that a given model will suffer. Okay. Okay, so let's see how to do it. We have to introduce some quantities which will be useful later on, also because they are connected to observations, so they are very important. They look theoretical based, but in fact they will be connected to observations. So suppose now that phi dot, double dot in absolute value, just to be sure, is much more than 3h phi dot 0, okay? So let's suppose that it is true, and of course, if the plateau is very flat, this will be true, of course. So the field has a small velocity, and also the acceleration will be even smaller. So this is called a slow roll condition. Okay. If that is true, then of course the equation of motion becomes 3h phi dot 0 equal to minus v prime, approximately. Okay, because I neglect the first term in the equation. And and then the condition, of course, phi dot 0 square much more than v, which is the condition that I impose in order to get p over rho equal to minus 1. I can get it from here, you see, because now this is of order of minus v prime divided by 3h. I can replace it here. So what I get v prime square divided by 9, h square, much smaller than v. But now the h square, if you remember, was 8 pi g Newton divided by 3 times rho, and I neglected the curvature term because in any case during inflation the curvature term is basically going to 0, as we have seen. And this is going to be more or less 8 pi g Newton divided by 3 times v, as long as the condition, this condition is satisfied. Okay, so now I can replace this to see what happens to the potential. So I get, from this relation, I get v prime square divided by 9. H square, I write it as 8 pi g Newton divided by 3 times v. I have another v here, so I put a v square here, and this has to be much more than unity. Okay? So you see the condition that I have is the following. Apart from the coefficients, so here you have a 3, for instance. Apart from the coefficient, if you remember that g Newton, roughly speaking, is 1 over m Planck square, I get the condition that v prime square times m Planck square divided by v square has to be much more than unity. So if you think in terms of as a unit of m Planck, you see this is a condition that tells you that the potential has to be extremely flat in units of m Planck. Okay, so when the field makes an excursion of order of m Planck, let's say, it does not have to see the change of the potential sufficiently in such a way that this condition is satisfied. If that is true, then I can use this equation, and I can impose this equation with inequality easily, and then I'm in this roll condition, and inflation is happening. Okay, this is more or less qualitatively what happens. But let me introduce now two slow roll parameters that will be useful in the following. Not only, as I said, theoretically, but also to connect to experiments, to quantify this. To say at least how much the potential has to be flat. So the first parameter, so those are the slow roll parameters. Okay, so there are two of them. People use different conventions, so let me state what they are. The first one is epsilon, which is minus h dot over h square. Okay? Of course, this parameter is also very small. Why? Because if during inflation the potential is very flat, the universe is expanding exponentially, the Hubble rate is very close to a constant as a function of time, and this parameter goes to 0 because h dot goes to 0. Of course, it's not exactly 0 because otherwise inflation will never end. And this parameter, if you remember h dot, I can also write it as minus 4 pi g Newton times rho plus p. Okay. But rho plus p in this case is, if you remember the definitions, so rho is at the, p is at the numerator, rho is at the denominator, so this is nothing else than minus 4 pi g Newton times phi dot 0 square, because the rho and the p, the potential has opposite sign, it cancels out, okay? So this parameter epsilon is nothing else than 4 pi g Newton phi dot 0 square divided by h square. And you see here, again, the condition of Zroll, because here h square is dominated by v, the potential. Here you have the kinetic term, and this number has to be much more than unity. Okay? So as long as epsilon is more than unity, then everything is okay. And I can also write down what is the physical meaning of this epsilon, because if I write down the condition, for instance, that a double dot is larger than 0, which is the definition of inflation, if you like, I repeat it many times. What happens is that you discover that this number is proportional to 1 minus epsilon. So when epsilon is more than 1, inflation is happening, and then epsilon equal to 1 dictates the end of inflation. So in a given model, when epsilon becomes equal to 1, you see here the kinetic term becomes of order of the potential, so inflation ends, because now p over rho is not equal to minus 1 anymore. And this is the point where when epsilon is equal to 1, this is the end of inflation. Okay? The way you derive this equation is, this thing is, of course, that you know that h is equal to a dot over a. You take h dot is equal to a double dot divided by a minus h square. Okay? So you see now you bring the a double dot divided by a is equal to h dot plus h square. But now you see that the definition of this is exactly equal to 1 minus epsilon times h square. So you see this is larger than 0 only when epsilon is more than 1. Okay? So this law of parameters, epsilon, is a crucial one, because not only it dictates the fact that the kinetic energy can be negligible, but also dictates when inflation ends in a given model. Okay? Again, this parameter depends on the model of inflation, because depends on the potential. Okay, so they're not universal numbers. It depends on the choice of your potential. There is another parameter which I want to introduce, another Zroll parameter, which is called delta. And this time, this parameter tells you how the acceleration of the inflaton field is small. So this parameter delta is equal to minus phi double dot 0 divided by h phi dot 0. Why this parameter is important? Because if you remember what I did, I neglect in the equation of motion the phi double dot compared to the friction term, and this tells you how good this approximation is. This parameter has also to be smaller than 1. Okay? Now, those are the definitions. So this one is delta, epsilon is minus h dot over h square. So those are the two definitions that I'm going to use from now on. Those parameters as function of time, during inflation they are both smaller than unity or much more than unity. If I use the equation, which is this one here, if I use this equation, you can show easily and I'm not gonna do it because it will take a little bit of time, but it's you can see easily that in fact the delta, well, let me start from the epsilon. The epsilon is in fact, in terms of the potential, you can express everything in terms of the potential. Um, um, well, that I already did because I did this computation here. In fact, it is here, okay? With the, of course, with the 9/3, the 8 pi g Newton, everything included. But let me introduce the delta, in fact, is equal to eta minus epsilon, and eta is defined to be the second derivative of potential divided by 3 times h squared. So sometimes there is some confusion in the literature, because if I express this delta parameter and the epsilon, those are the generic definition, the correct one, but sometimes people like to express these parameters in terms of the potential using the Zroll condition. So sometimes people put a V index here just to remember that in fact they are the same parameters but expressed in terms of the potential. But those are the correct definition that I'm going to use in the following. So we are not going to use this thing, but I'm just telling you because sometimes in the books or in the article you see this condition. So you can really compute these parameters in terms of the potential using an approximation. But remember, I will just use those for the time being. Okay, so let's forget about this. All right, so those are the two Zroll parameters. They have to be smaller than 1, both of them. And again, when epsilon is equal to 1, inflation ends. Okay, so that's what is more or less the dynamics. Okay, now suppose that during inflation, the universe expanding almost exponentially, almost because it's not exactly exponentially, because of course these parameters are never equal to 0 exactly. So let's compute now the total number of e-folds of a given model, given a potential, okay? So I give you a potential, whatever it is, and I ask you to compute how long it will last, okay? And I want a formula that express this number of e-folds in terms of the potential itself. So let's do this simple exercise. We want the number of e-folds. The number of e-folds, as we said, is n, is the integral from the initial time to the final stage in dt prime, let's say, well, dt because I can, times h of t. So this is what the number of e-folds is. Now what I do, I want to change variables now. So I integrate from ti to tf. And here, instead of dt, I divide by d phi times d phi times, well, let's put also the h of t times d phi. And of course, t will be a function of time, of phi, sorry. Okay, so now I'm using, so I can rewrite this as equal to the integral from ti to tf. I have d phi, let me put it here, and then I have h over phi dot 0, just to be sure that I remind myself that is the background value. Okay, and now I know that if I do so if I now use the Zroll condition, this is going to be equal to the integral. And here, since I changed my variable, in fact, I should write down this is phi I and this is phi f. So the value of the inflaton field at the beginning, at the end of inflation. So it's going to be phi I and phi f. And here I have d phi, my variable. And then I have h divided by minus 3 v primes divided by h. Because I remember what I used, the fact that 3h phi dot 0 in Zroll is approximately equal to minus v. Okay? So minus v prime, sorry. So there is a minus, sorry, this is a 3 here. Minus v prime divided by 3h. Okay? Which I rewrite as 3 h squared divided by v prime. And I also change the sign here, so I change the sign here. So this is phi f, and this is phi I. Okay? Yes, thank you. So this is the option that I have. I change the sign. And now what I do, I write this as an integral from phi final to phi initial in d phi. I know that h squared, I have 3 times, what is h squared? Is 8 pi g Newton divided by 3 times v. And here I divide again by v prime. So the 3 goes away. And so I have the integral from phi final to phi initial in d phi of 8 pi g Newton v divided by v prime. So this is the formula that tells you what is the number of e-faults in terms of the potential. You give me a potential, I integrate this ratio v over v prime in d phi. I multiply by basically 8 pi g Newton, which is 1 over m Planck square reduced. And then I compute the number of e-faults. Of course, I have to choose what phi initial is. We don't know, it's a value. But phi final will correspond to the condition epsilon equal to 1. Okay, so that's will give you the number of e-faults. Now, since I'm almost over before the break, let me just add one more thing, which is the following simple exercise. It will take me less than 2 minutes, because I just want to give you the flavor of what is going on. Suppose that v over v of phi 0 is the simplest potential you can write down, a free scalar field, like this. M squared over 2, where m is this mass of the inflaton, we don't know, times phi 0 squared, really the simplest one. Okay? So the potential looks like a parabola, something like this, which is of course very, very flat, because at the end of the day this potential, this m squared, is smaller than m Planck, much smaller than this. Now, in this exercise session, Matteo will show that the condition epsilon equal to 1 will correspond to a value phi final square, such that it is 1 over 4 pi g Newton. Okay, so it's basically of order of m Planck square. So the potential is very, very far from the origin, of order of m Planck. Now the question is, what is phi initial square? Well, of course you don't know, but you might say, let's be bold, and let's say that at the beginning of inflation, the typical energy that you have in your system is m Planck to the 4th. So let's suppose that for the time being, v of phi initial is of order of m Planck to the 4th, okay? The only scale you have in the problem. Then, apart from this small m, then of course phi initial square will be from here, I get m Planck to the 4 divided by m square. Okay, so this is much, 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 much larger than m Planck square. But of course I don't, you might think, but then I don't know what is going to happen at very large transplanckian energies, right? I mean, just you don't know. You say, we are used to say, well, the gravity is known up to m Planck, and then it becomes maybe quantum, we don't know, maybe it's replaced by string theory or whatever. But in fact here you have to remember that this phi squared is not an observable. What is an observable is the energy. So here I'm satisfying, in any case, the energy is up to m Planck, okay? Phi, again, is not an observable in this business. So what is going to happen is that now, if I compute the number of e-faults from this simple exercise, in fact, I should also tell you something that we will be clear in the following. M, if I want to fix the perturbations, so you have to believe me for the time being, is going to be about 10 to the 13 GeV. So you have to take it for granted for the time being. I will explain this number when I compute the perturbation. So I fix the amplitude, the steepness of potential in order to explain the perturbation that we see today in the CMB. So for the time being, you just believe this number. Okay, so you see this ratio is incredibly much larger than m Planck square by orders of magnitude. And then if you compute the number of e-faults, you see the number of e-faults will be dominated by phi initial, clearly, because phi initial is much larger than the phi final, which is only about m Planck square. So now if you do compute the number of e-faults, let's do it, and that will conclude the first part of the lecture today, because I want to promise you this number that is incredibly large. So, so what is the total number of e-faults? We said that is 8 pi g newtons times the integral. So the formula is there from phi final to phi initial in the phi of v over v prime, okay? V prime is m square times phi. So here you have 8 pi g newton integral from phi initial to phi final. No, sorry, from phi final to phi initial in the phi. And then I have v, which is m square times phi square over 2. Then I have m square times phi. You see the m square goes away. I have a factor of 2 that I annihilate here. It's 4 pi g newton. And then I have the integral in the phi of phi, which is 1/2 phi initial square. Okay, so that is the total number of e-faults. So this guy is, I multiply by 2, 8. So I get a 4 here. This is 1 over m Planck square. Okay, apart from the factor of 4, which is, as we'll see, is almost irrelevant. Phi initial is m Planck to the 4 divided by m square. Okay, so you see I have of order of m Planck divided by m, small m square. Okay, so we said that this is 10 to the 19 or 18. This is 10 to the 13. The ratio is about 10 to the 6. So this guy is 10 to the 12. Okay, so the number of e-faults in this simple model is not 60, but in fact is 10 to the 12. Okay, meaning that the omega minus 1, since it goes like e to the minus 2n, the omega minus 1 at the end of inflation, so we said f, is going to be e to the minus twice 10 to the 11, 10 to the 12. So now you can guess that this omega minus 1 will be 0 by a large amount. And of course, even today will be basically, omega will be 1. There is no way you can recover after inflation this growth of omega minus 1 to values different from 0. Okay, so that's a simple example that tells you that, in fact, inflation will make the universe locally extremely flat. Okay, so let me stop here. We take, I don't know, 10 minutes break, and then we will continue. Right? Thank you. You see? So what is going to happen is that the following. If I look at perturbations which are on long wavelengths, which I have, you know, that those are which I will be interested in from now on, I discovered that in fact if I look at different regions of the universe, let's say separated by some Abel radii, so those are small regions where the Abel radius is h minus 1 during inflation. The value of the phi field here is phi 0, let's say is some phi 0 here, and here it's again phi 0 up to a small fluctuations, which is proportional to phi dot, which is very small, because you remember during inflation phi dot is very small, the kinetic energy is very small. So the value is not exactly the same in all the regions. They are displaced by a given quantity which depends on the point, and also depends on phi dot. So in any case, there are small fluctuations. So what happens is that when inflation starts, it's unavoidable that different regions will acquire different values of the scalar field. Okay, you cannot avoid it. It's a quantum mechanical consequence, and therefore you create small inhomogeneities. Okay, if you look at different regions of the universe, the universe will look like the energy associated to the region will be slightly different, okay? As a consequence of the dynamics. It's not that you put it by hand. It is a consequence of the dynamics of the scalar field, okay? So that is more or less an intuitive way of seeing why the fluctuations are inevitably generated during inflation. Okay, this is a very intuitive argument. It's not even correct from the technical point of view because I forgot the fluctuations of the metric. I forgot a lot of other issues like the gauge invariance and so on, but let's go slowly. Okay, I will go back to these issues, of course, during the lectures. All right, so is it okay, this thing? Okay, very well. Now, so that was step number 1. Let's take step number 2, which is a little bit more formal, but not that much, as you will see, which is the following. I want now to consider a period of inflation, and I don't talk about the inflaton anymore. I take another scalar field, whatever it is. At the end, we will also identify with the scalar field of the inflaton, but for the time being, I want to be completely generic. I want to do an exercise which will be basically the cornerstone of all the cosmological perturbation. The moment you understand this exercise, you are done. Okay, you will understand the fluctuations generated during inflation. So the exercise is the following. I want to consider a scalar field in the sitter. So what is the sitter? Is the period where P over rho is exactly equal to -1, and therefore the scale factor is really something that goes like, let's say, a initial e to the h star t minus ti. It's exactly exponential, okay? So I want to do this example. Yes, thank you. So 10 minutes. So what I will do, I will first of all, so in order to specify the fact that the scalar field is not necessarily the inflaton field, I want to call it in a different way. Let me call it chi, okay? Chi of x and t. And also, this scalar field is massless, even though I will break this assumption later on. So the scalar field has a interaction like this, sorry, an action like this, -1/2 integral in d for x square root of -g times g mu nu inverse d mu chi d nu chi. Okay? So it's a massless scalar field that lives in a period of the sitter, so where the inflaton the scale factor is exponentially growing. And I want to look at what happens to this scalar field during this period. I want to see the fluctuations of a scalar field. I want to characterize the fluctuation of a scalar field. Once we learn what is the output, as I promised, you will see that we have learned basically 90% of the subject of cosmological perturbations. The rest are details. Okay, so this is very important and to stay with me. Okay, so what is the equation of state of this guy? It will be chi double dot plus 3h chi dot minus, of course, the Laplacian of chi divided by a square equals 0. So that's the equation of motion. Notice that here I'm not perturbing because that is the full equation of motion. Okay, I want to characterize the full thing. What I can do now, I can Fourier transform. I can write down chi of x and t as the integral in d free k. I want to divide by 2 pi over 3/2. That's the convention I'm using. E to the I k dot x times some function of time times the annihilator operator plus the Hermitian conjugate. Okay, I do the usual expansion in Fourier modes. And of course, since it's a quantum field, you have to impose the commutator, which is, the relation is chi dot times chi minus chi star dot times chi equal to minus I. Okay, so those are the usual commutator relation because it's a quantum field. But that's not going to play a crucial role for the time being. All right, so once we have this decomposition, the equation of motion becomes chi double dot plus 3h chi dot plus k square over a square times chi equal to 0. And also let me put a label chi here just to k here just to remind ourselves that we are in Fourier space. And what is k? Of course, k is nothing else than k is the modulus of this vector in 3 dimensions. So you have to compute the momentum, the corresponding conjugate momentum, and impose the usual commutator between, like in quantum mechanics, between the field and its conjugate. Okay, but it's not, as I said, it's not going to play any role. So I just mentioned it to rephrase the fact that it's a quantum field, but in general. Say it again. X. What is X? You are referring to this? Let me just, so chi dot chi minus chi, no, there is no chi here. Because this is a scalar field which is not complex, in fact. So they are in the, you know, they are in, no, but there is a complex thing which is here. Like this. Yeah, sorry, I forgot a star. Because in my mind, this scalar field is not complex, but okay. Okay, good. As I said, this condition, I just wrote it down in order to make it sure that it's a quantum field. But as we'll see, in fact, at the end of the day, everything is classical. But this will become clear in a while. Okay, so now this is a question of motion. So I want to study what is the solution of this equation. Again, I know the solution because in the sitter I can write down immediately the solution, but what I want to do is to look at the different cases. And then I will end because I had 5 minutes, okay? Very well. I want to do 2 cases. I mean, again, very intuitive, and then at some point we will be able even to solve this equation exactly with some boundary conditions. So I want to now do the following. Suppose that I'm doing the sitter. I have a period of, so the first condition, the first assumption is, so I have my region here of above radius h to the minus 1. And I consider the case in which the physical, the lambda, the physical wavelength of the scalar field goes like 1 over k, okay? And I want times a, because the physical one also scales like a, and I want this condition in which this is much more than h to the minus 1. So at the beginning, this fluctuation has wavelengths which are inside the above radius, okay? Because inflation starts, a is very small, so the wavelengths will be inside the above radius as kind of initial condition. And in this case, the equation of motion, if you look at this, since, of course, I have k over a much larger than h, so in fact, I can write down, therefore, k over a h much larger than unity. So I am physically in this condition. I can neglect in this equation this term here. Okay, so the equation of motion will become something like chi double dot plus k square over a square chi equal to 0. Okay, of course, here, this is not an equation of motion of an oscillator, but it looks like, right? Because you have a kinetic term and you have a frequency term, square, even though the frequency depends on the scale factor, therefore it depends on time. So you roughly, tomorrow what I will do, I will simply rewrite this equation in a simpler way. I will change coordinates in such a way to eliminate this time dependence. But you expect, roughly speaking, that your field, when the fluctuations are on sub-Hubble scales, so when the wavelength is much more than the Hubble radius, it will behave more or less like an oscillator, like a free oscillator. Okay, like a Klein-Gordon scalar field which has no interaction. All right, so let's go to the opposite limit, and then I will finish for today. In the opposite limit, when the scale factor starts growing, at some point the wavelengths will become larger than the Hubble radius. So the second stage will be when I have the Hubble radius, again constant, h to the minus 1, but this time the lambda, which goes like a divided by k, will be much larger than the Hubble radius, because the Hubble radius stays constant, but a grows exponentially. So at some point, the wavelengths of your scalar field will be super Hubble. Okay? What is going to happen is that in this case, what I do the opposite assumption, that I drop the k square with respect to the friction term. So the equation of motion will be chi double dot k plus 3h chi dot equal to 0. And what is the solution of this? Of course, there are two solutions, but one solution that I'm interested in is chi sub k becomes a constant. Okay? So what is going to happen is the following. Inflation starts, the scalar field is fluctuating because it has a frequency which depends on time. The fluctuations initially has a wavelengths which are inside the Hubble radius. The scalar field behaves like an oscillator. And then inflation goes on, the scale factor grows, the wavelength grows, because it goes like the scale factor. At some point, they become larger than the Hubble radius. At that moment, the chi field freezes in. So it does not evolve in time anymore. So here it's called freeze in, this moment. And the fluctuation in very large scales will become constant in time. Okay, it won't evolve anymore. And now you understand, you start understanding what is going to happen in this picture. So you start from some wavelengths which is really microscopic, quantum, okay? Then this fluctuation goes by e to the n. Sorry, not the fluctuation, but the wavelength goes to e to the n. And remember, n is 10 to the 12, whatever. Okay, so these wavelengths become larger, larger, and larger. It becomes on cosmological scales, megaparsec or so. And therefore, you see that the origin of this fluctuation on cosmological scales is in fact coming from the small fluctuation I had initially. And that's because the scale factor grows by an enormous number. So even though you have 10 to the minus 32 centimeter at the beginning, it becomes megaparsec easily, because you increase it by 10 to the 12 or so. Not only that, but it's important that this fluctuation becomes constant. They don't evolve anymore on super Hubble scales. Intuitively, you can understand it because, of course, the wavelengths, suppose that you have a wavelength here and then you have another maximum here. These 2 points are separated by many Hubble radius, so, Hubble radii, so that they cannot talk to each other. So that's the reason why it freezes in, does not evolve in time anymore. And then why it is an oscillator at the beginning is, of course, because when you look, even though you have an Hubble radius, suppose that you look at your system at very, very small distances, so wavelengths which are much more than the Hubble radius, you don't feel the curvature of your space-time in that region. So it's like Minkowski. It's like an oscillator. Okay, so that's the initial condition of the fluctuations. And then because of the expansion, they will go to cosmological scales. So what we will do tomorrow is to solve, in fact, this equation in the 2 limits by changing the coordinates. I will tell you how to solve this equation, and I will compute what is this constant. Okay? And once we are done with this, basically, we will be done with all the lectures. The rest will be details, very crucial details, but the notion of the cosmological perturbation is in this constant here that I will do tomorrow. Okay, so let me stop here, and I'll see you. Well, there is no exercise tomorrow, today, I guess, but we'll see tomorrow. Tomorrow we have 2 lectures, so plus the exercise. Yeah, tomorrow will be, you will be inflating all the time from all points of view. All right? Okay, thanks a lot.